Hello, welcome to The Naked Scientist this week with me, Chris Smith, and also with Dominic Ford. Hi, Dominic.
Hello, and in the show this week, power at your fingertips. Scientists have invented a new material that can generate electricity from the heat in your digits. Also, what the Large Hadron Collider is about to start looking for next, and how new types of LED are making it possible to transmit data through ambient lighting.
If you are sitting in an aircraft with a light above you, if you're in a meeting room with lights above the meeting table, then those lights are a means of communicating information, a potential supplement or replacement to Wi-Fi.
All illuminating stuff. Plus this week we're analysing asteroids. We'll find out where asteroids come from and is one about to collide with the Earth. We're also meeting the asteroid miners. There are companies out there looking to go prospecting in outer space. But how do you mine an asteroid?
If you would like to get in touch with us here at The Naked Scientists, email chris@thenakedscientist.com, tweet @nakedscientists, or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, first up, joining Dominic and me to take a look at the science news this week is science journalist Mark Peploe, Laurie Winklis, who's a scientist at the National Physical Laboratory, and also BBC broadcaster Victoria Gill. So let's kick off with you, Laurie. Thermoelectrics at your fingertips. Tell us more.
Yes, it's a really interesting paper that's just been published. It's a group of Korean researchers who've produced a flexible, thin-film thermoelectric device that can generate electricity simply by the heat from the heat produced by your fingertips.
When you say generate electricity, are we talking meaningful amounts of electricity?
Well, yes, meaningful in an electronic sense, shall we say. When they had these thin films of a polymer called PDOT, which is polyethylene dioxythiophene, what they actually applied one to a cooler, and then one of the brave researchers placed their finger on top. So very, very small temperature difference, about 5 degrees. And they produced about 600 microvolts of electricity. So a small amount, but that's more than enough to power a lot of today's sensors.
So how does this compare with what we can already do with things like thermoelectric generators? Because this is not a new concept, is it? I mean, this is 100 years old. People have been doing this for a long time.
Oh yeah, we've known about thermoelectric effects for even longer than that. But you can buy commercial devices and have been able to do so for probably about 60 to 70 years. And they've been used in the space industry ever since the Apollo missions. So yeah, you're right, the technology is not new at all. They compare in several different ways really to the commercial devices. Most of those devices use a semiconductor material, which is solid state. So there's no flexibility. And they're actually quite expensive to produce and can be toxic in some cases. These thin film devices, these PDOT polymer devices, are very cheap to produce. You can print them very, very cheaply and very quickly, and they're non-toxic. And they also have the added benefit of being a bit flexible. So although the power that they produce is a lot smaller, it just might be more suitable for some applications.
You mentioned sensors. What kind of devices do you see these things powering?
Well, I think the dream would be, that we could capture body heat by, collecting the body heat in a glove and powering your mobile phone or something. That would be the dream. But the reality is more likely that it would be something like a sensor on maybe the wall of a building. So it could be a structural health sensor, and it takes advantage of a temperature gradient, so a temperature difference between the surface of the wall and the air around the wall to actually power a sensor.
So they've got a really nice proof of principle there by the sounds of it. What have they got to do now before they can actually develop it to make something that's actually viable as a usable sensor?
They still have a little bit to go. Yeah, you're absolutely right, Mark. It's a proof of concept. But what they've done is they've tried to optimize the chemistry at this point. But they've actually produced quite large devices, so about 25 centimetre square devices, which is quite impressive. And as I said, you get a relatively useful amount of electricity from that. But from here on in, they really need to look at how they can produce them so that they're structurally safe. So you want them to be flexible, but you don't want the electrodes that you print on top. You don't want those to oxidize. So they have a lot of a bit more mass marketing to do, really.
Laurie, thanks very much. Well, let's go down on the very small scale, Mark, and a bit of particle physics. CERN has some stories to tell.
Yeah, that's right. It's quite a milestone week for the Large Hadron Collider at CERN, which is Europe's particle physics lab. in Switzerland. It's shutting down next week for about 2 years, and it's going to be upgrading so that it can smash protons with twice as much energy as it's been doing so far.
Is that really necessary? Because we've discovered the Higgs, we think, and actually at an energy that overlaps with the energy that accelerators we already had before we built the LHC could deliver. So do we need to go more powerful?
Yes, you thought we were all done, didn't you? But no, particle physics never ends. Obviously, last year there was this amazing discovery of something that is so like what was predicted to be the Higgs boson. You might as well call it a Higgs boson. But there's so much about it that physicists don't yet know. To be really sure that it is the Higgs boson that's predicted by theory, you've got to work out what its spin is, for example. They don't know that yet, and they need to keep taking more data about that. You need to know how it interacts with other particles. They just haven't seen enough of them to be able to see that yet. So by ramping up the energy, and they're ramping it up to 14 tera electron volts when they switch back on at the end of 2014, now that's quite a difficult number to get your head around, but what it actually means is that each bunch of protons is going to have the same energy as a motorbike travelling at about 100 miles an hour.
When you say that they're going to ramp the energy up, how do you get more energy out of a particle accelerator? How will they do that? What's physically involved, and why does it have to shut down?
You basically make the particles move faster and faster around it. They're already moving very, very close to the speed of light. At the moment, the particles are accelerated up to about 7 mega electron volts. This is with the huge superconducting magnets inside. Basically, you increase the magnetic field, you give them more pushes as you go around, and you just ramp up the energy. You remember E equals mc squared, 14 tera electron volts. Those protons are going to be 14,000 times heavier than a stationary proton.
Why do we need to shut CERN down in order to do that?
Well, you remember, last year was a triumph, but back in 2008, when they first fired the thing up, it was a complete disaster. It blew up shortly after they started it. There were some loose connections, basically. So they have to strip out about 10,000 of these big electrical connections and put new ones in. They're also taking the opportunity to put in a lot more electronics in the detectors that actually sense the particles. And this is one of the things that's going to allow them to gather much more data to try and probe new physics. Particle physicists are always looking for new physics beyond what they've already seen, and one of the big things they're going to be looking for sparticles. Are you going to ask me what sparticles are?
I just had some funny. I was thinking of Spartacus. I don't know. I think the similarity in the name, but what's one of those?
A type of particle predicted by something called supersymmetry. Our understanding of how particles work at that subatomic level is pretty good, but it can't really cope with things like gravity. It can't really describe gravity very well, and it can't even remotely come to comprehend dark matter, this unseen material that we know must be out there in the universe somewhere, because we can see it interacting with galaxies, but we don't know what it is, and our current theories can't describe it. Supersymmetry would be a way to resolve a lot of those problems. So far we haven't seen any evidence of it in the LHC, but with this upgrade you're going to be approaching the sort of energies where you really might get some clues to it.
There's also a mention in science of these sterile neutrinos. I'd never heard of a sterile neutrino. What is one of those, and what will the LHC be doing to try and find them? Why are they important?
Well, funnily enough, this is a project that, if it's approved, it's going to cost a lot less than the LHC. It's only going to cost about $110 million. That's about 70 million quid. And it could actually be up and running within 3 years. It's kind of an extension to a facility that they already have called the Super Proton Synchrotron. That actually feeds protons into the LHC. What they propose to do is to fire the protons out of that at a target. You make neutrinos. Now, the thing about neutrinos is they have no charge and almost no mass, so they hardly interact with anything at all. You've got billions of them streaming through you from the sun every second, and they don't do anything. They come in 3 varieties, 3 different flavours, and they can swap between them. And people basically don't exactly know how they do that. Sterile neutrinos have been proposed as a sort of intermediate. They help these different flavours to swap from one form or another, but nobody's really pinned them down. This experiment would propose to do that, to find that missing link in the neutrino flavour interaction.
So what more is there to learn about these different flavours of neutrino?
Well, one of the things that we don't understand, for example, is that why is it that more of one flavour called an electron antineutrino form from these flavour switching than all the other types? For example, I was talking about dark matter before. One of the things that they could find is that these sterile neutrinos, which you'd have to invoke to try and explain this flavour switching, they might actually account for a significant fraction of dark matter in the universe. So again, it might get at two different problems in physics through the same experiment.
Mark, thanks. Victoria, let's get a bit more biological. You've been looking at something on the brain.
Yeah, my brain is fairly boggled listening to all that particle physics. It's impressive stuff. But this actually comes from UCL, a really interesting guy called Professor Zecchi, who's Professor of Neuroaesthetics.
He used to teach me, actually.
Oh, is that right?
He did, yeah. He gave me some lectures on how the brain processes vision.
He is fascinating. And in the 90s, he started studying the sort of crossover between creativity and science, and sort of creativity and art and the brain. And he had quite a famous paper out a few years ago in PLOS about a centre for beauty in the brain, which is the orbitofrontal cortex. So a bit of your cortex just behind your eyes, which is where the orbito comes from. And it's a very misunderstood, or, well, very little understood part of the brain. And he basically ran an experiment where he put people in an MRI scanner so you could see sort of activity in their brain, and he showed them pictures that they perceived as beautiful, that they judged to be beautiful, and he played them music and asked them what they thought of it. And when they thought the music and the paintings were beautiful, the same part of their brain was activated. And now he's moved that forward in a paper in the European Journal of Neuroscience, where he's asked people to judge whether a painting is more beautiful than another, and he's seen these certain areas of the brain activate. So he's asked them to make a judgment. And what he's done is compare that to a judgment about just a pure sort of perceptual judgment, where he said which painting is more brightly coloured. And there's a completely different set of centres of the brain, a completely different set of networks activated when we look at aesthetics and experience beauty.
What's in the pictures? Is it pictures of people, or are they pictures of landscapes, or has he compared that? Because there might be a subtle difference in how the brain relates to faces and people, or just things around us.
Exactly. And yeah, he's addressed that in this paper, and it is a bit of an open question. So he's looked at portraits and landscapes and a huge variety of different pictures to try and sort of cancel out that issue. So that's hopefully we're not just responding to faces in an emotional way, as you rightly say. That's going to activate your brain in quite a different way. But this is quite an open question. He's seen these networks activate. The orbitofrontal cortex seems to get activated again, and seems to be quite important when we're looking at two paintings and saying one is more beautiful than the other, whether it's a portrait or a landscape. But it really is almost completely silent when we're just making a judgment based on this is a brightly coloured picture and the other one is not so brightly coloured.
So the brain has a beauty centre, obviously something that will light up in your brain when you look at me. But what's the point of it from an evolutionary point of view? I mean, why have a beauty centre or a beauty detecting or a beauty acknowledging part of the brain?
Well, Zecchi's quite interested in how this might actually help people with affective disorders, where they cannot sort of process this idea of sort of experiencing a reward from something being beautiful and pleasurable. I mean, he's interested in the fundamental questions of sort of how beauty and art kind of activate our brain, and he kind of looks back into the humanities and philosophy to see what great philosophers have said about how we respond to things and how we think. And he's trying to apply those huge questions about truth and beauty and creativity to biology to actually look inside people's brains. But in actual fact, there are very little understood parts of the brain, like the orbitofrontal cortex, that clearly have an important role in making us feel good. And if that's something that a problem is caused with when we have an affective disorder like depression, then this actually could be something that helps people in the future, that gives us a way to sort of treat people more specifically when they suffer from things that really make their life not as enjoyable.
Well, let's hope so. Thanks, Vic. Well, sticking with the brain, I've got one interesting study here. It's in the journal Neurology this week, and it's by Jean Schoenen, who's from Liège University in Belgium. And he and his colleagues have published this paper showing that you can prevent a proportion of migraines in people who suffer them regularly with cutaneous electrical stimulation delivered to the forehead. So they took 67 regular migraineurs, people who had regular disabling migraines, divided them into two groups, and having asked all of them to keep a diary for about a month beforehand of how often they suffered migraines, so they had a sort of baseline for this, they then randomly allocated them to receive either real treatment or sham treatment. There was no obvious difference between the two arms of the trial, so The people who were getting the sham treatment didn't know, it was blinded. But the people who had the real treatment were applying this sticky patch to the skin for 20 minutes every morning onto their forehead, and it was delivering about 16 microamps of current into the skin and stimulating the trigeminal nerve that supplies the head and face. And they then asked them to follow up for 90 days, logging how many migraines they had. The results are stunning. 30% reduction in migraine days in the people who got treated, compared with no difference in the people who had the sham treatment. And this was mirrored by a 37% reduction in the use of drugs, which I think is absolutely amazing, really.
Wow, that's incredible, because migraines are so distressing for people. But I thought they were to do with inflammation. What do they think that the cutaneous electrical stimulation is doing?
Well, the argument behind migraines is that this is a neurovascular phenomenon. You have abnormal patterns of brain activity which initially cause you to get the wavy lines across vision, which characterises the onset of a migraine, and this then triggers painful dilatation of blood vessels and stimulation of nerves in the meninges, the pain-sensitive layers around the brain. And so by applying this sensory stimulus, they don't know exactly how it works, but they think that the input of that energy into the sensory system might in some way disrupt the establishment of these abnormal patterns of brain activity and thereby abolish the migraine getting established. But it's certainly an initially very interesting and exciting starting point, and given it's so cheap and simple and totally non-invasive and harmless, it's effectively the same as the TENS machines that we use when people are having babies, for example. Very effective, very safe, much better than drugs, none of the side effects. Anyway, let's look at dinosaurs now, talking about big impacts. Dinosaurs and what wiped them out, Dominic.
That's right. A bit later on in the show, we're going to be talking about the potential hazard that asteroid impact poses today. But first, I've got a new story about the asteroid impact 66 million years ago that might have caused the dinosaurs to become extinct. Now, this was a period in the Earth's history called the Cretaceous-Paleogene boundary, 66 million years ago, when there were quite dramatic changes to life on Earth. There's fossil evidence that about 75% of species became extinct in a period of about 1 million years. But the puzzle in recent decades has been to try and work out what exactly caused this event. And an asteroid impact has been strongly implicated, partly by looking at the types of life forms that were most seriously affected. The plants were quite seriously affected, and that would suggest they were having trouble photosynthesizing. Now, an asteroid impact would have thrown large amounts of material into the Earth's atmosphere and potentially blocked out the sun's light. And also cold-blooded creatures like dinosaurs, who rely on a hot climate, would also have been badly affected if the sun's light was being blocked.
Well, sounds pretty simple. I mean, what's the contention?
Well, in fact, there's been a bit of a problem with the timescales, because people have identified a particular crater in Chicxulub in Mexico, which is about 66 million years old. This appears to be the crater created by an object about 10 kilometres across, which would have blown up with a power of about 2 million nuclear bombs. And that's about the power you would have needed to wipe out the dinosaurs. But this crater seems to be slightly too young. It appears to have formed about 200,000 years after the dinosaurs were wiped out, so it can't have caused that event. Now, Paul Rene from the Berkeley Geochronology Centre and his colleagues around the world have done a new dating on this crater. And what they're doing is they're looking at fragments of rock from this impact. They're actually looking at argon gas, which is trapped in that rock. And this is formed very slowly by the radioactive decay of potassium, which takes place over tens of millions of years, and it gradually builds up in those rocks. And it's not in the rock to begin with, so by seeing how much argon there is trapped in that rock, you can roughly date when it formed. And so he's got a new estimate of how old this crater is.
And what does that show?
And what it shows is it's towards the end of this mass extinction, but it's there in the period when creatures were becoming extinct. And so it suggests that, yes, there were other stresses on the dinosaurs. The Earth's climate probably was cooling down by about 10 degrees C in a space of 1 million years. That caused stress for creatures like dinosaurs. But it was this meteor impact at the end that wiped them out completely.
So we're now satisfied we've got a new strand of data that seems to give much stronger evidence that this was responsible, and it's within the time zone. It's not 300,000 years out of date. It's actually on top of the time when the mass extinction was happening. So it's much more closely aligned in time. So it does fit.
Yes, I mean, it would have been a tremendous coincidence if this meteor impact hadn't triggered the dinosaurs to become extinct. But now the evidence all seems to fit together rather nicely. And so this is temporal with the plants dying out and with the dinosaurs dying out.
Thank you, Dominic. And thank you also to our news guests this week, Mark Peplow, Laurie Winklis and Victoria Gill. And incidentally, you can find the references and the transcripts for the news stories that we've been discussing this week on our website. They're at nakedscientist.com. And it's well worth looking at the site because it's had a major facelift, largely thanks to Dominic. It's now a real wonder to behold. This is The Naked Scientist with Chris Smith and with Dominic Ford. If you'd like to get in touch with us with any questions or any comments, you can email us. It's chris@thenakedscientist.com. You can tweet @nakedscientist, or you can find us on Facebook.
Still to come, how some companies are making plans to mine asteroids. And will plants grow on Mars? We'll hear from a NASA scientist about how to make a mini Mars to find out.
And that's the planet, not the Mars bar. Now, first off, you've probably heard of wireless communications, or Wi-Fi. They use radio waves and microwaves to send information. A spin-off of that Wi-Fi is Li-Fi. This is a system that uses visible light to send information into mobile devices and computers. But now a consortium of UK universities is working on a way to take Li-Fi to a whole new level. The EPSRC's Jane Reck has been talking to the scientists behind this project.
Imagine that where we have light sources, street lamps, traffic lights, shopping windows. Light is everywhere, and let's imagine a scenario that all these light bulbs are sort of high-speed wireless transmitters that connect either humans with humans or systems with systems.
This whole area of Li-Fi, of using visible light for communications, is based on the very recent emergence of light-emitting diode technology as the source of lighting.
Tiny LEDs are being developed that could simultaneously do many tasks, such as deliver internet connections, display information and provide lighting. It's the next stage in research to use visible light to transmit information. Professor Harold Haas from the University of Edinburgh is one of the partners in the project.
Li-Fi stands basically for light fidelity, and what it essentially means is that we take the new generation of energy-saving light bulbs, which are made of light-emitting diodes, LEDs, and we use them for illumination and data transmission. And not only data transmission, but very high data transmission. So we envisage that these light bulbs will in the future achieve 1 gigabit per second, and that is several times faster than a typical Wi-Fi system in a home can provide.
The tiny LEDs being developed are made from gallium nitride, a man-made semiconductor material whose properties are ideal for high-power, high-frequency use.
The name it's called ultra-parallel. That means we have a parallel transmission. And the idea is sort of take many small devices where each small device is capable of transmitting very high amount of data, much, much higher than a single LED, a large LED can do. Take these sort of high-performance little LEDs and put them into large arrays so that parallel transmission is ongoing.
Professor Martin Dawson from the University of Strathclyde is leading the project. He explained more about the novel aspects of this research and how Li-Fi will complement our existing communications systems.
One of the benefits that Li-Fi gives is it's bringing in a new region of the spectrum, so it's adding spectrum to the available bandwidth for communications. Wi-Fi is clearly a very, very successful technology, but there's been raised concerns about possible health issues. I should emphasize there's been no evidence of any negative effects from this, but it remains a concern. If you're communicating with light, with visible light, then there is no concern about that. So this is one of the aspects. There's also security aspects. It is possible to tap into microwave and radio broadcasts in a way that you cannot with visible light. It can also be deployed in situations where it's not safe to have microwave or radio waves present, and that could be in an operating theatre, for example. It could be in a submarine or in an aircraft. So if you look at the light-emitting diode that might be on your Christmas tree or in a torch, for example, if you looked at that under a microscope, you would see that The size of the chip in there is about 1 millimetre square. It's a sizable component. What we're talking about is basically dividing up that active area into many thousands of much smaller elements. These individual elements that we call micro LEDs or micro LEDs are human hair size. Individually, they're on the micrometer scale, and when you shrink down the size of the devices, there are effects that come into play that offer you the possibility of switching them on and off much more quickly. And it increases the bandwidth, the on-off switching capability and speed, but some other beneficial characteristics start to come into play as well. When you do that, you give the possibility of sending independent communications signals from each individual element in the array. You not only have many, many hundreds or potentially thousands of separate individual lighting or communications channels that you can start to play with independently, but you also have a means to communicate optical images at the same time. This is the key element of novelty here.
With each tiny LED acting as a separate communication channel, Martin explained more about the sort of tasks that could be carried out simultaneously.
If you are sitting in an aircraft with a light above you, if you're in a meeting room with lights above the meeting table, then those lights are a means of broadcasting and communicating information, a potential supplement or replacement to Wi-Fi, and we're expecting this to come in relatively quickly. There have been a number of demonstrations of this already all over the world. Our devices offer a potential means to increase the data handling capability in that type of application. We still have the capability to do lighting, but a means to communicate much higher quantities of information, so to download video information very quickly, for example.
This consortium of researchers also involves the universities of Cambridge, Oxford and St Andrews, with funding from the Engineering and Physical Sciences Research Council. The project brings together expertise from the areas of electronics, computing and materials. It's thought that Li-Fi could be in widespread use within a decade.
Jane Reck, and there's also an audio slideshow on this story on the EPSRC YouTube channel. You can find that at youtube.com/EPSRC video. We'll also put a copy of that video on our website, nakedscientist.com.
Time now for this week's Planet Earth. Avian pox affects a number of bird species, but it was discovered in the UK's population of great tits in 2006. As avian pox is spreading, scientists are monitoring birds using trapping and ringing in order to study the disease. Sue Nelson visited the Whitham Field Station in Oxfordshire, where she met the field manager Ross Crates and Oxford University's Dr. Shelley Lakish.
It's actually a very distinctive disease. The birds develop large sort of tumour-like lesions. They develop them on the head, particularly around the beak and the eye area, but also on their legs and on their wings. And basically when we catch the birds and we have them in the hand, if they have a lesion, it's very hard for us to miss it.
Walking down the extremely muddy path.
We've actually got the mist net set behind the feeder. As we're walking down to it from here, we can't see it, but we can certainly see that we've caught a few birds in it. Looks like there's about 7 or 8 at the moment.
It looks like we've got a nuthatch as well, just behind the cage there.
Ah, right. So you've got several great tits.
Lots of blue tits.
Lots
so
of blue
most
tits,
of these
I
ones that
recognise
we're
them.
looking at here are blue tits. Then there's a nuthatch there.
2 nuthatches.
And a coal tit.
Aren't they gorgeous?
So this is a good example of a retrap here. So you can see it's metal ring on one leg and it's passive integrated transponder on the other leg. Just a little plastic ring
it's
here.
got little tiny rings on each leg, yeah.
So what we do is we have antenna on our feeders and on the nest boxes, and when the birds come to feed or come to their nest boxes, we can record them without having to be there at all.
We've got 2 little white bags now with the birds in, and you're putting all the birds in little bags.
Yeah, so here's another one that's already, we've already caught this one previously. So he has a little black pit tag on his right leg and a metal silver band on his other leg. So we can look up the number on that ring and we can find out all the history about this bird, where he was caught last time, how much he's grown, and whether he was breeding the last time he or she was caught. And we tally that information up, and that feeds into our records. He's still pecking me. And avian pox is actually, we have noticed in all of these species, except for the nuthatches, but it's by far more prevalent in great tits than any of the other birds, and we're not actually sure why that is, and that's one of the things that we would like to find out.
Right, well, I will let you continue extracting the birds and bagging them before we head back to the table.
So now we have our birds in their little bags hanging here waiting their turn to be processed, and so one by one we'll go through, we extract them from the bags like I have done with this little blue tit, and I have it in my hands now, and now begins the process of ringing and pit tagging and measuring. And so the first thing we always do is put on a ring, because that's the identifier for the bird.
You've just affixed that
I've
deftly. So will you check in future now to see whether, when you catch a bird that has been previously tagged and ringed, whether it has the virus or not? All those birds that we trapped looked quite healthy to me.
So at this time of year, we do expect avian pox prevalence to be very low, because it is a vectored disease. It's mosquito vectored, and winter is not a very good time for mosquitoes to be around.
Do they all die, or do some survive?
We've had 105 cases of avian pox in great tits, at least in this wood, and some extras in some blue tits and other species. And we've seen 14 of those have been recaptured again, and they've been asymptomatic, so they haven't had lesions, whereas they did previously. And so we do know that recovery is possible, but our analyses are also telling us that this disease definitely kills the birds. It reduces the survival rate of individuals.
And what have you discovered so far in terms of how far this virus is spreading, while you quickly measure its wing, the blue tit's wing there?
The disease arrived in England, in the southeast of England, around the East Sussex area, and that was in 2006. And since that time we've seen it spread westwards right into Wales, and as far north now as around the Mersey River, around Manchester region. So it has really spread quite a fair distance in just a number of years.
Is there anything that can be done at the moment other than monitoring it and studying it?
That's our key focus at the moment, is to track its spread, to know exactly what we're dealing with, in the sense of whether we are dealing with something that will eventually be population-wide amongst the great tits. But we are also continuing to look at genetic studies to try and isolate, further understand where the disease originated from and how it's mutated in and suddenly appeared in this great tit population.
Dr. Shelley Lakish from the University of Oxford ending that report from Sue Nelson. And you can hear a longer version of that interview with loads more bird action on the Planet Earth podcast. Simply follow a link from our website or find it via Planet Earth Online.
You're listening to The Naked Scientists with Chris Smith and with Dominic Ford. Now, next week, Earth will have a truly close encounter. Asteroid 2012 DA14, which is a lump of rock weighing somewhere around 130,000 tonnes, will pass just 24,000 kilometres from Earth. That's closer in than many satellites. Objects like this are known as near-Earth objects, and they're of interest to scientists, but also to a group of entrepreneurs who are aiming to mine asteroids for their minerals.
We'll hear from the asteroid miners Chris Lewicki and Rick Tomlinson in just a minute. But first we're joined by NEO specialist Dr. Simon Green from the Open University. Now, first of all, Simon, what do we mean when we talk about asteroids?
Well, asteroids are lumps of rock which formed in the inner solar system but never developed into a planet. So they're essentially the building blocks of terrestrial planets like the Earth.
And some of these are classified as near-Earth objects. Is there a strict definition of what that means?
Yes, anything that comes within 1.3 astronomical units, so 1.3 times the distance of the Earth from the Sun, is classed as a near-Earth object. Most likely an asteroid, but it also could potentially be a comet.
And roughly how many objects are we talking about in that category?
How long's a piece of string? It depends on the size. We know of about 10,000 objects at the moment, but that's just a tiny fraction of the total population. The smaller you go, the more there are. And so there are many millions down to sizes of metres.
And I guess the big ones are quite easy to see, but the smaller ones are much harder to pick out.
That's right. The larger ones are tracked. We probably know of 90 to 95% of all objects bigger than about a kilometre in size. Of things bigger than maybe 100 metres or so, we certainly know less than 10% of them.
So how do we go about looking for them?
With telescopes is the best way, using wide-field CCD cameras and tracking the sky and looking for objects that move. So essentially you look for objects that produce trails and images, or look like stars but are changing position from minute to minute. And from the changing position you can calculate the orbit.
So if you got a near-Earth object and you're perhaps slightly worried that it might come into a collision with the Earth, how do you go about knowing how it's going to travel through the solar system in the future?
The orbits themselves, you can calculate and predict where an object will go if it doesn't have any other forces than gravity acting on it. But you need enough observations in order to track its orbit as it is now, and then you do calculations based on the perturbations from other planets, other asteroids, and the predictions are fine until you have a close encounter and a near miss with a large body, and then it's very, very difficult to predict afterwards. So we can predict for objects when they might come close to a planet, but after that we probably don't know. Now, most near-Earth asteroids, because they're in the inner solar system, pass close to planets at some point. Their orbits are not stable over long time periods, so they probably only exist in the inner solar system for between 1 and 10 million years.
Now, the object 2012 DA14, which is coming close to the Earth next week, weighs about 130,000 tonnes. How dangerous is an object that large?
This is actually the very bottom end of the kinds of objects that can penetrate the atmosphere and reach the ground. It's around 45 metres if you do the calculation, and it's possible, if it's very fragile, that it would explode in the upper atmosphere, much like an object in 1908 that damaged a large area of Siberia, fortunately with no people in. If it's solid iron, which might have come from the core of a larger asteroid, then it would certainly reach the ground and make a crater maybe 100 metres or larger in size. But this is at the very bottom end of the sort of damage scale, if you like, that we need to be worried about.
Now, we heard earlier about the asteroid that might have wiped out the dinosaurs. If we were to find an object that was quite large coming towards us, what could we do about it?
Something that big would be quite tough, but we probably know that that's not going to be the case. But something maybe a few hundred metres in size up to a kilometre, we would need to be able to try and deflect it. And we need to therefore know its orbit and predict where it's going to go with many years, preferably decades ahead of time. We can then use a number of different techniques. It might be a kinetic impactor, firing a spacecraft into the target that produces a tiny change in its momentum and therefore its track, but magnified over a number of years, it can be enough to miss the Earth. Or we could use something like a gravity tractor, where you bizarrely use the gravity of the spacecraft itself, take it close to the object, and then fire the rockets very, very gently, and use that small gravity of the spacecraft to just gradually change its orbit. Now, both those techniques will take a long time, and we may not have that level of warning. In the end, probably the only alternative is to let off nuclear weapons very close to the object, vaporising some of the material, and the jet effect can then move the target.
Well, I guess it's reassuring to know that those options are there. Thank you very much, Simon. That's Simon Green from the Open University.
Now, the majority of the asteroids we're acquainted with have come to us, but now a number of enterprising individuals are developing ways to harvest and mine asteroids for the minerals that they may contain. Chris Lewicki is the president and self-appointed chief asteroid miner at the Seattle-based company Planetary Resources, Inc., and Rick Tomlinson is the chairman of Deep Space Industries. We'll come to Rick in just a second, but let's kick off with Chris. First of all, Chris, why do you want to mine asteroids? What's the appeal of doing that?
Well, asteroids are a very exciting destination in our solar system. And from the intro that you just heard from Simon, of course, they've been out there for some time. They're the leftover things that formed our planets, and they have a number of very useful and very valuable resources on them that will be important not only here on Earth, but as we continue to expand out into space.
When you say resources, what sorts of things are we talking about that we can get from an asteroid that we may not be able to obtain more easily on Earth?
Well, the resources that you may consider bringing all the way back to Earth are such elements as the platinum group metals. And these are elements that during the formation of the Earth actually sunk down to the core and are relatively depleted on our planet. There are other resources, though, in addition to those that are equally exciting. things like the iron, nickel, and cobalt that can be used for the manufacturing of space structures. And then a very important resource to us all in space is water. And we have enough water here on the planet, and we would never bring water back to supply Earth from space. But not having to transport that water out into space is very valuable, and to be able to use the material that's already out there in space is really the great opportunity that's awaiting us.
How much have you had to raise to get your venture going in the first place?
Our company's been around for a few years. We just announced ourselves last spring. And in starting any venture as audacious as asteroid mining, you certainly require a lot of money and some visionary individuals who are willing to take that first step. So we've been very fortunate to get gentlemen like Eric Schmidt, the executive chairman, and Larry Page, the CEO of Google, as well as other Americans like Ross Perot, and two-time spaceflight participant Charles Simonyi. And they've given us a great start down this path of building really a new industry and the next phase of space exploration.
And Rick, what evidence is there that this is a viable business proposition for both Deep Space Industries, your company, and also for Chris Lewicki, I guess, your competitors?
Well, let's put it this way. As Chris was mentioning, the large early market for us is going to be what we do with these resources in space. And if one looks at the current launch costs, if listeners were to walk outside of their homes and grab a pound or a kilo, let's say, of dirt, if that were delivered in space right now, that would be in the range of $10,000 for that to be carried into space. And that's just dirt. So pretty well anything that you can provide up there, any resources or materials that we can create in space are going to be valuable. On Earth, we measure ore in a few $1,000s per tons of ore. In space, the value of it goes up incredibly. And once we begin to provide those resources in space and begin to learn how to refine and process them, then we can begin to build different sorts of structures. We can support missions. Let's say the space agencies want to go to Mars. We can be their oasis. We can provide hardware using some of the manufacturing processes. So there's a wide range. And then there'll be the kinds of activities that begin to spin back to the Earth, whether it is shipping down platinum, etc. We're not so focused on that. But basically, at the core of it, we have to admit that Chris and their founders and our founders are true believers that this is the next frontier. And we've got to figure out a way to make it pay, or nobody stays. No bucks, no Buck Rogers. So
Indeed.
We're out there working that.
Well, let's talk practicalities for a second. So, Chris, where are you going to get these asteroids from?
Again, as Simon described, we have almost 10,000 objects that have been discovered to date, many of them in just the last 15 years, that are orbiting the Sun in relatively close proximity to Earth. And in many cases, these near-Earth asteroids are even more accessible and easier to travel to than it is to land on the surface of the Moon. Actually, about 15% of them, or almost 1,500 objects, a relatively easy journey away from what we have learned about robotically exploring space in the past 50 years. So what is necessary in the next few years is to really identify those worthy candidates that have the appropriate resources on them, that have the appropriate orbits and a schedule to get to and from them, and to begin and continue to develop the technology and the business environment to develop and produce these resources to a market.
And Rick, how are you actually going to get to these objects, and then once you get there, get stuff off of them, and then what are you going to do with it?
The two companies, of course, have different approaches. In our scenario, we're launching small prospecting probes called Fireflies, or about the size of 3 laptops, and they'll do flybys and begin to help us characterize or learn what the different types of asteroids are made of, so we can compare that with observations made here in the Earth or using Hubble or whatever. Then we will send out what we call dragonflies, which will bring back a few kilograms so that we can begin learning how to utilize the materials and probably sell a little bit of that to scientists. Once we get to that point, then we get into what we call harvesters, which are using different sorts of thrusters, ion or plasma thrusters, fairly small relative to the size of the asteroid, but it doesn't take much. If you push a little bit over a long period of time, you can move something very large a long distance. As Chris was saying, once we're in space, we can do a lot that you can't do if you have to go down into what we call a gravity well, such as on the Moon and Mars. Once we're out there, if we have the time and the patience, we can move very large things very long ways. So, for example, we might move an asteroid into lunar orbit. And there, if anything goes wrong, it falls harmlessly on the Moon. So it's not a safety issue. And then we can begin extracting and the actual industrial process.
It's reassuring to think that you've thought about what might happen if you accidentally create a giant traffic jam or a collision in space. Chris, is there not a good reason to say take the refinery to the asteroid and then bring back just the stuff you want?
Well, certainly there are a variety of options that we can have. We too, like Rick had mentioned, are in the prospecting phase of sending out the geologists, so to speak, to these things to identify the resources, and then through a stepwise process, continuing to educate what it will take to acquire the resources, what the resources exactly are, and then, as you said, decide whether the next most appropriate action is to bring some of that resource back to the Earth's proximity, where you might have a few more kind of infrastructure available to help develop it, or in other cases, do some local refining of the resource kind of at the asteroid and then just ship back to the point of use, whether that's a fuel depot in Earth orbit or a developing space station, or maybe even destinations in the future out to Mars and elsewhere, that you would just send really something that is closer to a finished good or a raw material.
And just to finish off, what is the timescale on this? I mean, Rick, when are you aiming to actually have things airborne and samples coming back?
Our goal as a company is to try and get something popping up around 2015, the actual Fireflies. And part of that is to demonstrate our capability, to demonstrate the technology, to start testing them, and seeing how operable they are. The actual large-scale mining activities, I don't know exactly Chris's company's schedule, but I don't see that happening until 2020 and beyond, the serious mining sorts of activities. But keep in mind, even here on Earth, if somebody's pondering a large-scale project, be it a major dam or mining or other large-scale project, timescales of 10 years or more are quite common. So it's not that out of the range.
And in the meantime, you might be able to help Simon, because if he finds something that he needs moved out of the way and you've got your spacecraft good to go, you might just be able to help him out. Thank you very much, Rick Tomlinson from Deep Space Industries and Chris Lewicki of Planetary Resources, Inc. You're listening to The Naked Scientists with Chris Smith and with Dominic Ford.
Now, our solar system contains a great diversity of objects, from the Earth we're standing on to asteroids that, as we've just heard, there are companies hoping to mine. These objects range from massive gas giants like Jupiter right down to clouds of microscopic dust. But we're not sure how it all formed. Research using computer models is helping to shed some light on this problem, and to find out how, Ben Valsler spoke to Alan Jackson, a PhD student in the Institute of Astronomy in Cambridge.
I've always been interested in how did Earth get here? Why do we have this nice planet we live on? How do we actually end up with planets like Earth? Are there likely to be any others?
Are there any examples out there in the universe that we can actually use to see this happening, or do we have to rely on what we see here in our own solar system and extrapolate backwards?
There are some places where we think terrestrial planet formation is going on. All of this is quite new in terms of people going out and looking at it, so we're fairly certain there must be places that it's happening, and we're still trying to find them. The first exosolar planet around a star like our Sun was, I think, 1995. So it's really not all that long ago at all.
So that's not given you a lot of time to find examples that you can use?
No, exactly. And well, the first one was in 1995. I think the second one was in 97. It's only really in the last 10 or 15 years that it's really beginning to pick up speed.
So, in the absence of systems that we can look at and watch it happening, how do you actually start to understand the processes that are going on?
If you can't see it going on, then what you have to do is look at what you end up with We know to a reasonable degree what they must have started like, because we can see protoplanetary disks that are these big disks of dust and gas that are around young forming stars. How do we get from that to planets?
And how do you fill that gap in? What do you have to use to actually start answering that question?
Lots of computer simulations for the very early stages where you're looking at the gas and dust and how that gas and dust starts to collapse down to produce you some little asteroid-like objects. Because that's mostly gas, you're really looking at fluid-type situations. Later on, when the gas is gone and you just have lots of bits and pieces of rock that have stuck together and you've got various different sized lumps, then you're looking more at just simulating those individual particles and colliding them with each other.
So you have to rely on some basic physics to tell you what should be going on.
Yeah.
But then it must be very difficult to integrate and to work out when we stop using the physics of fluid dynamics and we start using gravity and other accretion models.
It is, yes. It's getting the boundary between them is quite difficult. Sometimes they don't quite match up properly. It's not particularly uncommon for people or different groups to be simulating different aspects of the evolution of these type of things, and the results of one group's doesn't quite match up with what the other group's doing. Basically, you just need to talk to each other and try and work out what's causing it to not match up. If you can do that, then do it again. Does it match now? Yes, good. No, okay, maybe not. We just try again.
So that way, lots of different groups all over the world can actually refine their models until we come to an understanding of what we think really has happened.
Yes, and then of course there's the observational side, which is now we need to try and go and find something out there that's in the process of doing this and see if it actually looks like that.
This is obviously a very good way to make very well-refined models that show how this cloud of dust and gas becomes the planets and the objects that we know about. But unfortunately, things are never quite that straightforward, and we know from looking at the planets in our solar system that there's been some almighty collisions and hails of new objects. How do you account for the actual quite destructive nature of our solar system?
It's one of the big problems, actually, with these things, is getting the planets to not just blow each other up. And actually, it's with the smallest objects that there's the biggest problem, because obviously the smaller something is, the less gravity it has. So getting them to stick together without destroying each other is quite hard. Once you get up to things the size of Earth, although you do get these incredible collisions that are very, very violent, because the Earth is, comparatively speaking, quite big and has a lot more gravity holding it together, it's a lot more difficult to actually completely destroy it. It can happen, but it's a little bit more difficult to do.
How do we account now for the diversity of objects that we see in the solar system? So we have gas giants, we have terrestrial planets like Earth and Mars, but we also have these bands of asteroids that clearly haven't accreted into a planet in the same way that Earth has. How can the models make sure all of those fit and are in the right place?
Well, so with the asteroid belt, the main reason that we have the asteroid belt is Jupiter. If Jupiter wasn't there, or hadn't formed where it is, then probably the asteroid belt would either have accreted onto Mars, and so Mars would be bigger, or it would have formed a fifth terrestrial planet. But because Jupiter is so very massive, it stirs up the material nearby to much higher velocities, so that early process that I mentioned, where trying to get little things to stick to each other is a bit more difficult, it just doesn't happen.
Alan Jackson from Cambridge University.
And to finish this week, Question of the Week time, and Hannah Critchlow has been finding out how to make a bit of space in her kitchen.
This week, we're brought down to Earth. Logan wrote in with this question, asked here by Georgie.
I want to be a space scientist when I grow up. First, I want to do an experiment at home. I want to find out if we can grow plants on Mars. So to test this, how can I make a small Mars at home?
So, can you make a miniature Martian environment in your kitchen and try and grow plants in it?
My name's Chris McKay. I'm a planetary scientist with NASA Ames Research Center. I'm interested in Mars and particularly the question of life on Mars. The question for today is, can plants grow on Mars, and how could we simulate that here on Earth? Well, I think there's two parts to that question. The first part is the soil on Mars. Could plants grow in that soil? Well, the best analog we have on Earth for Mars soils is volcanic rocks, soils that have been produced from volcanic rocks. So we could go to Iceland or Hawaii and collect some soils that have come from ground-up volcanic rocks and use those as Mars analogs. And folks have done that. It's a pretty easy experiment to do. Try it. I think you'll find that most plants will grow fine in that kind of soil. The other question, though, is about the environment of Mars. The temperature is very low, the atmosphere is very thin, and the atmosphere is carbon dioxide, very different from Earth's atmosphere. We can simulate those in the laboratory, of course, with a vacuum chamber and a big freezer. You can get a sense of how to simulate those at home in your freezer. It's cold, not as cold as Mars, but almost as cold as Mars, and certainly too cold for plants to grow. We can also simulate the low pressure by taking a small jar, putting water in it, boiling the water, which would drive off the air, drive away the air, fill the atmosphere with water. If we then seal the small jar and cool it, the water will condense, creating pressures very much like the atmosphere of Mars. So we can create low-pressure environments, put it in the freezer, now you have low-pressure cold. If we wanted to have CO2 in that as well, instead of water, maybe we could try something like carbonated drink, like Sprite. Then as it boils, it'll put out water and CO2, drives away the air, we seal it, the water condenses, creating the low pressure, and there's a small amount of CO2 left. Voila, a little bit of Mars. In the freezer, low pressure, cold. Plants won't grow in that. We know that in order for plants to grow, it's got to be a little thicker, a little warmer, maybe something in the refrigerator instead.
So it is possible, to some degree, to emulate a miniature Martian environment at home. And on the forum, Clifford Kay and Evan A.U. add that, although not strictly speaking a plant, Antarctic-dwelling lichens can cope with low temperatures. Next up, we question everlasting love.
Hello, Naked Scientists. This is Michael from Winston-Salem, North Carolina. With divorce rates being over 50%, is monogamy for humans a natural need, which is nature, or a societal concern, which would be nurture?
So many other species have multiple partners, but are humans meant for monogamy? What do you think about that one? You can post on our Naked Scientists Facebook page, you can tweet at Naked Scientists, you can email Chris at thenakedscientists.com, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow. That's it for this week. Thank you very much to our guests, Simon Green from the Open University, Rick Tumlinson of Deep Space Industries, Chris Lewicki from Planetary Resources, and Alan Jackson from Cambridge University. The production this week was by Hannah Critchlow and by Ben Valsler. Next time, we're tugging on your scientific heartstrings to celebrate the science of love. Do try and join us. This programme comes to you from Cambridge University, and The Naked Scientist is supported by the Wellcome Trust and the EPSRC. I'm Chris Smith, and thank you for listening. Goodbye.